Hello everybody, my name is Alex Block, and today I'm here to present locally decodable / correctable codes for insertions and deletions. This is joint work with Jeremiah Blocky, Elena Grigorescu, Shaban Kulkarni, and Minchin Zhu. I will mention for the purposes of this talk, we only talk about locally decodable codes, and mention that our results extend to the locally correctable setting as well. So a brief overview, we will have an introduction to what's happening, we will go over our result, we will go over a toy problem that is heavily related to our result. We will then discuss this NoisyBinary search algorithm and then give our construction. So the introduction. So to begin, the focus of this work is on insertion deletion codes, or install codes for short. These are error correcting codes which are resilient to adversarial insertions and deletions. So if I have an input message X, I encode it with my encoding function enc, I obtain some code word C. Now, this code word is run through an adversarial insertion deletion channel. So this is different from the normal Hamming adversarial channel in the following sense. So you can insert garbage values. So these red C tildes are garbage values. You can see that bits C2 and C3 are swapped. You have C7 has been completely deleted and C9 has been repeated. And C5 is just out of place. And in particular in this setting, we still ask the decoder, when given this corrupted code word C tilde, to output the initial message X. So for our setting, we are really interested in the local decoding variety of install codes, or LDCs for installs. So if we take the same partial picture as before, so I have an input message, I encode it, I run this encoding through the adversarial channel, now we have that in this setting, the decoder is only expected to decode one symbol of the initial message at a time. So in this picture, this means that, okay, the decoder now says, I want to decode index I, so I'm going to output xi. And further, the decoder is no longer given explicit access to the corrupted code word C tilde. Instead, it is given oracle access to this code word. So in order to decode index I, it's going to make some oracle queries and then output xi. Okay. A bit more formally, a code C with encoding function enc 01 to the k to 01 to the n, and note this extends to any alphabet sigma, is a q delta epsilon LDC if there exists a randomized decoding function decoder such that for all input messages X, for all indices I, and every corrupted code word that is delta close to the encoding of X, the decoding function makes it must queue queries to the corrupted code word, and the decoder will output xi with probability at least half plus epsilon. Okay. Now, if delta is the fractional Hamming distance, then we say C is a Hamming LDC, and if delta is the fractional edit distance, then we say that C is an install LDC. So very briefly, I'll discuss some LDC design goals. So usually we want low query complexity, we want a high error rate delta, we want a large success probability epsilon, and we want a large information rate k over n. So these are all conflicting design goals with different trade-offs. However, we will not be discussing this in this work. So the study of codes for installs was initiated by Levenstein in '66, and I should note that this is in the non-locally decodable setting, and since then, these objects have been extensively studied. In particular, the locally decodable variety have only recently received attention, and in our work we revisit one of these results, in particular the result of Ostrovsky and Paskin-Chernavsky, so OPC15. So OPC15 give a compiler to obtain install LDCs from any Hamming LDC. And what we do is we provide an alternate proof of this result using different combinatorial techniques. So what is our result? We give a generic compiler that transforms any Hamming LDC to a binary install LDC. So in particular, given any q delta epsilon Hamming LDC over an alphabet sigma, from sigma k to sigma n, there exists a binary install LDC with the following parameters. The query complexity is q times polylog n, where again, n is the encoding length of the Hamming LDC, so we only have a polylogarithmic blowup. The code is resilient against theta delta fraction of install errors. The success probability is only reduced by a negligible amount. And the code word length is n times log sigma. So in particular, if sigma is a constant size alphabet, we obtain a constant information rate. So, brief overview of what we do. Let's first look at our encoder. So our encoder follows the well-known idea of code concatenation with a few modifications. So let Cout be the given Hamming LDC that we're given as input, and let Cin be some insertion deletion code. For us, it's going to be the known Shulman-Zuckerman install code. So first, we use Cout to obtain an encoding of a message X as a code word C. So then we take the encoding C and divide it into equal sized blocks. Then each block is appended with its index. So the first block is given index 1, the second block is given index 2, and so on and so forth. Now each indexed block I is encoded as YI using Cin. So this is the inner insertion deletion code. Then we surround each YI with buffers of zeros. And finally, we concatenate all these buffered blocks into a single code word. Okay, so the encoder is not doing anything fancy. It is doing something more or less standard, but some issues are going to arise in the decoder. So the decoder is given oracle access to some corrupted code word y tilde. It's given an input index I, and it must output xi. So recall that we're given oracle access to this corrupted code word, and that this corrupted code word is a corruption of a concatenated code word. So there's all these concatenated buffered blocks, which were themselves inner encodings. So we're given oracle access to a bunch of these inner encodings of the inner code. So given this oracle access, in order to decode xi, it suffices to simulate the oracle queries for the outer Hamming LDC decoder. However, the issue here is we need to find the correct code blocks in order to simulate this oracle access. But how do we do that? So the broader picture is on input index I, the outer decoder has some indices it needs to look at for the whole Hamming LDC code word. But each of these indices ends up in some block because we blocked up the output of this Hamming LDC. So we have to find where these blocks are in the final corrupted code word. So to understand this problem and how to solve it, we are first going to examine a toy problem of searching in an almost sorted array. So first, a definition. An array of size n is delta sorted if it becomes sorted, say in ascending order, after removing at most delta n elements. For example, in this list, sigma, it is 0.3 sorted because we can remove 6, 10, and 2 in order to make the list sorted again. So this induces the problem of tolerant searching. So as an input to this problem, you input a delta sorted array, sigma, with the value x. And as output, you are going to ask it to output sigma I equal x. You're going to ask it to output index I such that sigma I equals x, or bot if the list does not contain x. So there are various models we can look at for this setting, but of particular interest to us is the query access model. So we have oracle access to elements of the array, and our goal is to minimize the number of queries to get an output. So this is the problem considered by Finci and Italiano, and I'll mention some remarks first. So we need randomness. If our algorithm is deterministic, we can't really do better than omega n queries. The classic binary search algorithm works when delta equals 0, and it also works in the testing variant. And finally, it is impossible for sublinear time algorithms to find every in-place element. So what does this mean? If I look at the set of all of the elements that would remain if I remove the delta fraction of elements that are corrupted, it is impossible to find all of these elements in sublinear time due to the result of Finci and Italiano. So in the worst case, searching in this delta sorted array requires omega n queries. And I will briefly remark that there are various related but different notions of tolerant search in the literature. The one of Finci and Italiano is of interest to us. So what do we do? So we need sublinear query complexity, ideally polylogarithmic. So we relax the problem as follows to aid in our goal. So we have a relaxed tolerant searching problem where the input's the same, a delta sorted array, sigma, and a value x we're looking for. The output's going to be the same. where the index I, such that sigma I equals x, or we're going to output bot if x isn't in the list. And now we have two goals. So the first goal being the same as before, we want to minimize the number of queries to this list. And second, we want this probability to be small. So what this probability says is that if you are looking for sigma I, the probability you output bot, given that sigma I is in the list, is at most 10 delta. Another way of putting it, looking for any sigma I, you succeed with probably at least 1 minus 10 delta. So this relaxed variant of tolerant searching allows us to obtain a randomized algorithm which does the following. So there exists this randomized algorithm such that for any delta sorted array sigma, there exists a set of indices with the following properties. So first, the set of indices is large. It is most of the set n. Second, for every element I in S, the probability that the algorithm outputs I when given as input sigma I is at least 1 minus negligible in n. And this assumes that sigma I is actually in the list. And finally, A has query complexity log cubed n. Okay, so this is some polylogarithmic query complexity. And we remark by union bound that we also conclude that for all I in the probability that for all I in S, A on input sigma I equals I is at least 1 minus negligible in n. Okay, so by examining this relaxed version of this problem, we're able to circumvent this lower bound due that we saw before of omega n. So this algorithm is actually what we call a noisy binary search algorithm, which I'll now discuss. So with an example by picture, suppose we are looking for x equals 3 in the following array. So this is the same corrupted array we had before. So what the noisy binary search does is the following. It starts with these left and right pointers L and R, which induce some middle section of the array to search in. So how you should think of this is you ignore the first third in front of L, you ignore the last third behind R, and you take samples of the center part. So in this picture, we're going to take log squared n number of samples in this red portion, and then we compare it to the item we're searching for. So how do we do this comparison? Well, we take the median and then we recurse. So if the median is larger than x, then we recurse on the left. And if the median is larger or smaller than x, then we recurse on the right. What does recursion do here? It throws out everything either before this red section or after this red section. So in this case, we're going to recurse on the left, which will induce L and R as this, and induce this new red region, which we're going to also sample log squared number of samples. Okay, and then so on. We keep recursing until L and R are close enough together to exhaustively search this entire interval for the element x. Okay, great. So the noisy binary search algorithm, in more detail, is exactly as I said. So it has oracle access to the array sigma, and it has a key x given as input that it's searching for. And we want it to output I such that sigma I equals x, or we want to output bot. The parameter t here is just the number of samples we ask it to do at every step before recursing. So now in this function, if L and R are within constant distance of each other, we just read the entire interval and output accordingly. So if sigma I equals x is in here, we output the correct I. Otherwise, we output bot. Otherwise, there are these M1 and M2 that we derive based on the pointers L and R, and we draw random samples from this interval. And then, given all these samples, we take the median of these appropriate sigma samples, and we recurse accordingly, given a comparison to the median. Okay, great. So what does this noisy binary search do for us? So first, we note that we obtain the query complexity of log squared n per iteration, just by choosing t to be log squared n. And there are log n many iterations because during each step of the recursion, we're throwing out a constant fraction of the array. So now the algorithm successfully finds x if the following two invariants hold. So first, during each iteration, x lies between L and R. So X has to be in this. We have to maintain this invariant. Otherwise, the algorithm will not find X. And second, in each iteration, the sigmas you sample have to, the sigmas in the interval you consider have to contain a bounded number of corrupted elements. However, item 2 does not hold in general. The density of corruptions can increase during each iteration. So what do we do about this? We're actually able to argue that enough of these elements of item 2 are good elements. So not necessarily contain a bounded number of corruptions, but enough of them are good. What does this good mean? So to do this, we introduce the notion of locally good indices. So suppose S is the set of corrupted indices. So an index I, any index I, is locally good, is alpha locally good with respect to the set S if the following holds. Every neighborhood around I has a bounded number of corruptions. So in particular, it has alpha fraction of corruptions. Okay? Otherwise, we say I is alpha locally bad with respect to S. Okay. So the key observation here is that when an index I is alpha locally good for a suitably small alpha, the noisy binary search algorithm will find sigma I equal X except with negligible probability. And I want to briefly remark that this notion of locally good is used in the design and analysis of depth robust graphs, which are a combinatorial object that have found many applications in cryptography. So what's our main theorem for these indices? Suppose the set of corruptions has size at most delta n. Then at most 2 delta n over alpha indices are locally bad with respect to S. So this means that most of the indices are locally good, which is what we need for our invariant. So to prove this theorem, we first define a notion of forward-backward locally good. This is a very simple notion. An index I is forward locally good with respect to a set S if all neighborhoods in front of I have a bounded number of corruptions. And analogously, we have backwards locally good if all neighborhoods behind I have a bounded number of corruptions. Okay, and the key observation here is alpha locally good follows if and only if forward and backward locally good follow. Okay, so given this definition, to prove the theorem, it suffices to show that there are at most delta n over alpha forward alpha locally bad indices. Okay, and then by symmetry, we obtain that the number of locally bad the number of backward locally bad indices is the same. So to see this, first consider I1 as the smallest forward locally bad index and let W1 be its witness. So what does this mean? That I1 to I2 ... to W1 contains more than alpha fraction of corruptions. Inductively, we keep choosing these pairs IK, WK as follows. You choose IK to be strictly larger than WK minus 1, and as the next smallest forward locally bad index, and let WK be its witness. So you end up with a picture like this. I have I1 to W1, I2 to W2, I3 to W3, ... all the way to ISWS. Say there's S of these things. Okay, so the first key observation is that every locally bad index must be contained in one of these red intervals. Suppose not. Suppose there is some locally bad index here. Well, by the induction step, we would have chosen this as our first locally bad interval, as our next locally bad interval, with some other witness W'2. So it has to be the case that we chose that I2 is the next one. Okay, so given the fact that all bad indices must be in these red intervals, we can count them. So the number of bad indices is at most the number of elements in all of these intervals summed together, which is again upper bounded by the size of the set intersection over alpha, just by definition of being locally bad. And then we have that the summation has to be less than the size S, the corruption set S, which is less than delta n. And we obtain our result by symmetry. Okay, so what's our construction? So briefly going over the encoder again, in a bit more detail, we have an input message, say X. It is encoded as a length M outer encoding. This is the Hamming LDC we're given as input. We divide this encoding into log m size blocks. We append an index to each of these blocks. We then apply the inner encoder on each of these indexed blocks. We then append buffers between all the blocks, and then we output this as the final encoding message. Okay, so now what about the decoder? So now the bottom level, we replace the output with the corrupted code word. And suppose I'm asked to find index I. So via the outer decoder, this induces some indices, say J1, J2, J3 in this outer encoding, which we now need to find. So if we just focus in on J1, in the blocking phase, J1 propagates to this block, which in the append index phase propagates to this block, which in the inner encoding phase propagates to this block, which we need to feed to the inner decoder in order to obtain the index block again. And then this block will correspond to this buffered block, which now we need to find in the corrupt code word. So how do we do this? Well, we're actually going to use the noisy binary search idea here, but for a corrupted code block instead of just corrupted indices. And now we'll talk about the differences between these two algorithms. So the actual decoder versus the toy problem. What happens? So first in the toy problem, each element corresponds to an array symbol, whereas in the decoder problem, each element corresponds to an index block of code word bits. In the toy problem, the corruption of the corruption corresponds to out of order elements, whereas in the decoder problem, corruption corresponds to blocks with a high density of insertion deletion errors. Okay? So thus, if we remove delta fraction of elements from either of these cases, the remaining elements are sorted. So remember, we have in the decoder problem, we have a concatenation of encoded indexed blocks. So if you remove all the corrupted elements, you have an in-order set of index blocks. Okay? So in the toy problem, we are able to sample random elements and directly read them, but it's not so simple in the decoding problem. So we're able to sample random indices, but then we have to do this local searching in this in some interval around this index in order to find a code block that contains this indice in order to decode it. Okay, and our locally good property allows us to do this with high probability. In the toy problem, error density corresponds to the fraction of corrupted indices, whereas in the decoder problem, error density corresponds to the fraction of bad blocks weighted by their lengths. Okay, so the corrupted blocks. And then finally, the base case of the toy problem, we read the entire interval to locate x, and in the decoder problem, it's somewhat similar, except reading the entire interval plus an extra step, what we call a buffer finding algorithm, which is a modification of the buffer finding algorithm due to Shulman-Zuckerman. And we do this to look at all good blocks within and decode each of them to figure out if we have the correct index. Okay. So that's all I'm going to talk about in this talk. I'd like to thank you for your attention. If you would like more details, please see the full version here on arXiv. Thank you very much.